But for now, I want to introduce this idea of the division algorithm, okay? So what the division algorithm states is that if n and d are positive integers such that n is greater than or equal to d, then it's always possible to find non-negative, so positive or 0, integers q and r such that n is equal to d times q plus r, where r is less than d. Okay? So this is saying a bunch of random complicated stuff. Can someone decipher it for me? You know what we can do? Let's assign names to each of these terms. So what's n? What's d? What's q? And what's r? In terms of something you might have heard of before. Yes, in the back.
So like numerator, denominator, quotient, remainder.
Okay. So I'll give you the last two. Quotient, remainder. I guess you can think of n and d as being numerator and denominator, but I'm looking for a different term. Yeah.
N is the dividend, and
Yeah.
is the divisor.
Dividend and divisor. So what this is saying is if you want to divide n, which is some dividend, by some divisor d, you can always write n as your divisor times your quotient plus a remainder. Okay? And this is something that we've seen many times previously in the course, right? Suppose we wanted to represent the set of all possible remainders when we divide by 3, right? We wrote x as either 3 times some quotient, or 3 times some quotient plus 1, or 3 times some quotient plus 2. Is that clear? And in each time, the remainder was less, the remainder is always less than the dividend, right? So when we had our, the remainder is always less than the divisor. So here, when our divisor is 3, the remainder is either 0, 1, or 2. Is that clear? Okay, so this is basically just a complicated way of saying, if I want to divide 25 by 7, I get 3 with a remainder of 4. All this is saying is I can put this together formally as 25 is equal to my divisor, which is 7, times my quotient, which is 3, plus my remainder, which is 4. This is just a complicated way of putting that into words. Any questions with this? So this is called the division algorithm. Okay? And as you'll see, especially when we get into solving modular equations and doing modular inverses, this will be very important. Any questions? Cool. So the next formal definition that I want to cover, we sort of assumed it already, but you just want to have it down. We say an integer n is greater than 1 is prime if and only if its only factors are 1 and n. And if factors are something other than 1 and n, so i.e. if it has something other than 1 and n as a factor, we say it's composite. And 1 is neither prime nor composite. Okay, and we'll see why in the next slide. And as we saw in homework 5, we did a proof that there are infinitely many primes. Okay? So here's a question. To check if some number n is prime, the naive way would be to check all numbers between 2 and n minus 1 and see if they divide. Right? Because the definition of a prime number is a number such that the only factors are 1 and n. So we check everything from 2 to n minus 1. But can you think of a better way to do this? Yes? Yes, so that's a good point. And so that actually leads into something that's called, I believe, the sieve of Eratosthenes or something. Has anyone heard of this before? Okay, so it's this algorithm that you can use to go through and remove all the multiples of 2, and then all the multiples of 3, and so on and so forth. And you will see what all the prime numbers are up until some certain point. Okay? And maybe I'll link something on the homework that you can go check out. But that's not exactly what I'm trying to get at here. So again, pretend my question is, given some number n, I want to tell if it's prime. What's another way I could do this? Instead of checking all the numbers from 2 to n minus 1, what could I check? Yeah?
You can check up to the lowest integer less than square root of n.
Okay, so could also check So we can say floor of square root n. And why is that the case?
Because if we say that a number m
Yeah.
is a factor of n,
Yeah.
then n divided by m is also a factor of n.
Okay. So that's like saying if 2 is a factor of 24, then 24 divided by 2 is also a factor of 24. Okay?
So 12 is a factor of 24. So if we have already found one factor on this side of square root of n, then we've also found another factor on the other side of square root of n. So we don't need to do all the computation of n minus 1. We can only check up to square root of n, and we'll have factors.
Exactly. So for example, let's just write out the sets of factors of 24. Okay? So 24, I could write it as 1 and 24, 2 and 12, 3 and 8, 4 and 6. Okay? And I could, write 6, 8, 12, and 24. That's sort of redundant. And so what the idea is, I only need to check those three numbers, because I wouldn't check one, right? I only need to check the numbers that are less than the square root of 24. Because for every factor that's less than the square root of a number, there's a factor that's greater than the square root of the number. Is that idea sort of clear? So all this is saying is you only need to check the first half of the factors. You only need to check up until the square root of the number. Any questions with that? So if you want to do some sort of naive test, like, I don't know, you want to see if 47 is prime. You don't have to check all the numbers from 2 to 46. You could stop checking at 6, right? Because that's the ceiling, that's the floor of the square root of 47. Because the square root of 36 is 6, 49 is 7, so it'll be 6 point something, so you check up to 6. Is that clear? Any questions with that? Cool. So now here's another formal definition, the fundamental theorem of arithmetic. So the fundamental theorem of arithmetic says two things. One, that any integer greater than 1 can be written as a product of prime numbers, and two, that this prime factorization is unique. Okay, so it says two things. Every integer can be written as a product of primes, right? If the number itself is prime, the prime factorization is just the number itself. And the prime factorization itself is unique. Okay? So based off of this definition, the question I have for you is, why do we not say that 1 is prime? Like, why is 1 neither prime nor composite? Yes?
Then you can just add like an infinite number of ones.
Exactly. So let's consider the prime factorization of 5. Well, 5 itself is prime. So, I mean, that's the prime factorization. But if 1 was prime, these would all be different prime factorizations. Those would all be different because the exponents are different, right? So for this reason, we don't count 1 to be prime. But let's say in general, I want to prime factor a number. How can I go about doing that? So let's pick the number, I don't know, 360. How do I prime factor this number 360? Any ideas? Yeah?
Factor tree.
Pardon?
Factor tree.
Sure, you could do a factor tree, but that takes up a lot of space. Has anyone seen the way where you draw this vertical line next to the number? How many people have seen that before? Okay, a few. So what you do here is you draw this vertical line next to the number, and you start by looking at the smallest factors of the number. Okay? But there's a special case. If there's a 0 at the end of a number, what do you know has to be a factor? 10. So what do you know also have to be prime factors? 2 and 5. So on the left, I'll write 2 and 5, and now I'll write the result I get when dividing 360 by 2 and 5. So now I'm at 36. Okay? Now what's the smallest prime number I know that goes into 36? 2, right? So I'll write a 2 on the left. I'm left with 18. What's the next smallest prime? 2 again. So I have 9. What do I have with 9? 3 and 3. So now I just read the numbers on the left column. So I take everything here, and I'm left with 3 2s, 2 3s, and a 5. Is that clear? So to prime factor a number, I write this vertical stick next to the number, For every 0 I have, I count a 2 and a 5 and I truncate a 0. And then I just look at 2's first. When 2's no longer divide the number, I look at 3's. When 3's no longer divide, I look at 5's, and so on and so forth. And of course, you can simplify wherever you see common things that you might know. So for example, at 36, instead of manually dividing 2, 2, 3, 3, 36 is 6 squared, which has to be 2 squared times 3 squared. Is that clear? You got a question?
I was just going to say for 18.
Yeah.
We could have said 3 instead of 2.
Yeah, it doesn't change anything. So the order itself doesn't matter. That's just one way of doing it. But basically, you look at your number and keep dividing up prime factors until you're left with 1. And at 9, after I remove 3 and 3, I'm left with 1. So then I'm done. Then I read my prime factors from the left column. Any questions with that? Okay, so we've established why we say 1 is not a prime number, and we've sort of reviewed how to prime factor a number. Okay, and if you are still rusty or just haven't seen this idea of prime factoring a number, we'll add some practice problems on them. Sound good? Okay, so this is a question I want you to work on with the people around you. It was on a phone interview I had for a quant trading position on Friday, so it's hard, but I think it's interesting. So what's the smallest number whose digits multiply to 10,000? Okay, so I'll give you a couple minutes to work on it with the people near you. I think it's an interesting question. And yeah, we'll talk about it.
So you want your 3 on 1 plus 1. Factors.
Okay, let's come back together. So did anyone have an approach on how to solve the question? Smallest number whose digits multiply to 10,000. Yeah. Okay, so one guess would be, or one approach would be to just prime factor 10,000. But we know 10,000 is 10 to the 4, right? But 10 is just 2 and 5, so this gives us 2 to the 4 times 5 to the 4. Okay? So the first number you might think of is 22225555. Is that clear? 22225555. And then when my interviewer, I said this result, and my interviewer asked, how confident are you? I said something like 95%. And then his question was, what is the smallest number whose digits multiply to 10,000? Or sorry, not 10,000, 20. Okay, so if we look at the case for 20, how do you prime factor 20? 2 squared times 5, right? 2 squared times 5. So then the most basic guess would be what? 225, right? But why is that obviously not the answer? Because you could do 45, right? And 45 is, of course, smaller than 225. So we can use the same logic with 22225555. Right? We know we can't combine any 2 and 5, because that'll give us, that just won't work, because the digits have to be up to 9. So how can we combine some of these 2's and 5's so that we have a number that's smaller than 22225555? So one possibility is you combine these two 2's and these two 2's, right? So you have 4, 4, 5, 5, 5, 5. But why is that still not the smallest? Yeah. Exactly. So the way to get rid of the most digits as possible would be to do 2, 8, 5, 5, 5, 5. Is that clear? And if you play around with this for a bit, you'll notice that there's no way to reduce any more digits. Okay? Because any two of the digits you have right there, when you multiply them, you will get a number that is greater than 9. Right? So after we write our prime factorization 2, 2, 2, 2, 5, 5, 5, 5, the question is, how many digits can we reduce such that all of our products have to be less than or equal to 9? Okay? And we combine 2 of the 3's into 1 8, right? Because 2 times 2 times 2 is 8. And so now we know our digits are going to be 2, an 8, and 4 5s. So now the question is, how can we rearrange these such that it's the smallest possible number? And how would we do that? Right, we write the digits in ascending order. So what we would do is put the 2 at the front, the 4 5s, and the 8, right? Because if we reverse this order, we would get the biggest possible number. Well, not the biggest possible, but the biggest in that case. Right? Because we'd have the 8 at the front. But since the way numbers work, the numbers at the front have the most precedence, we want to put the smallest numbers at the front, largest at the back. So the smallest possible number is this right here. 2, 5, 5, 5, 5, 8. Okay, so now we want to talk about this idea of greatest common divisors and lowest common multiples. Okay, and so this is probably an idea you've talked about before, but my guess is that you probably didn't see these formulas before, right? And so the GCD of two numbers, A and B, refers to the greatest common divisor, i.e. the greatest factor that is shared between both numbers. And the LCM refers to the lowest common multiple between A and B. So the LCM is the smallest number for which both A and B are factors. Is that clear? Okay, and so we have this weird verbose definition, which says that if A is a product of some n primes with exponents c1, c2, all the way till cn, and B is a product of the same primes but with different exponents, we say that GCD is the product of the same primes but with the minimum of each exponent, and the LCM is the same product but with the maximum of each exponent. Okay? So looking at that definition is not that useful. Okay? So first I want to work on a smaller example, and then maybe we'll look at the one we have here, 1200 and 2520. Okay? So why don't we look at the numbers 10 and 24. Okay? Actually, you know what? To make it interesting, let's do 16 and 24. How can you prime factor 16? 2 to the 4, right? And how do you prime factor 24? 2 cubed times 3, right? Because it's 8 times 3. Any questions with that? So 2 cubed times 3. What do we already know is going to be the greatest common divisor? Greatest common factor? 8, right? Because 8 is a factor of 16. It's a factor of 24. You could really write all the factors out of 16 and 24 if you wanted, and you'd see that 8 is the smallest one that satisfies both. But let's use this formula, okay? So we have the GCD of 16 and 24 is equal to 2 raised to the min of 3 and 4 times 3 raised to the min of, that should be a 3. 3 raised to the min of 0 and 1. Is that clear? Because 24 has a factor of 3, but in 16 we could implicitly write a 3 to the 0 because it doesn't have a factor of 3. Is that clear? And then what's the min of 3 and 4? Of course it's 3. What's the min of 0 and 1? It's 0. So it's just 8. Is that clear? So does everyone see why this formula sort of makes sense? Because we want the largest number that is a factor of both. Okay? Any questions with this? How many people have seen this before, by the way? Okay, so not too many. Why don't we look at the lowest common multiple of 16 and 24? What do you guess the answer is going to be? Yeah, 48, right? Because 14 times 2 is 16 times 3 is 48. So what would happen? What's the LCM of 16 and 24? Well, it's 2 raised to the max of 3 and 4 times 3 raised to the max of 0 and 1. What's the max of 3 and 4? Well, it's 4, so we get 16. And what's the max of 0 and 1? It's 1, right? So we get 16 times 3, which is 48. So this matches what we would guess intuitively. Yeah?
I don't have the intuition why it works.
Okay, does anyone have a potential explanation as to why this works? Like, where did this come from? Yeah. Sure.
Okay. So if so, just going by this example, we see that 16 has like 4 2s inside it, and like 24 has only 3 2s inside it, and 24 has 1 3, but 16 has no 3s. So if we're looking for a number that divides both of them, and we're looking for the largest number that divides both of them, then we basically want to find the largest number of 2s and 3s that you can put in that number, right? So
Yeah.
you can only put 3 2s in that number and still have it divide both. And you can only put 0 3s in it and have it divide both.
Yeah, so that perfectly explains why. Okay? So 16 has 2 4s and 0 3s, or sorry, 4 2s and 0 3s, and 24 has 3 2s and 1 3. So for the GCD, we're trying to maximize the factors, like we're trying to find the largest factor that is shared by both. So one number has 3 2s and the other number has 4 2s. So what is shared by both? 3 2s. Is that clear? If we picked 4 2s, 2 to the 4 is not a factor of 24, but 2 to the 3 is a factor of both. Okay? Because we need it to be a factor of both 16 and 24, so we look at the exponents on 2. In one case we have 2 to the 3, in the other case we have 2 to the 4. The largest one that is shared by both is 2 to the 3, so we take 2 to the 3. For the next exponent, 16 has 0 3s, and 24 has 1 3, right? So we need some number of 3s that is contained in both 0 and 1. So what's the largest number that is contained in 0 and 1? It's 0. Does that make sense? Right? And we do the exact opposite for the lowest common multiple. Right? We want the smallest number that is both a factor of 2 to the 4 times 3 to the 0 and 2 to the 3 times 3. Okay? So that's why when we look at the exponents 2 to the 3 and 2 to the 4, 2 to the 3 is not a factor of 2 to the 4. So the smallest number that's a factor of, 2 to the 3 is not a multiple of 2 to the 4, right? So when we're looking at 2 to the 3 and 2 to the 4, 2 to the 4 is the smallest number that's a multiple of both. Similarly, when we look at 3 to the 0 and 3 to the 1, 3 to the 1 is the smallest number that's a multiple of both. So that's why for the GCD, for each exponent we take the minimum, and for the LCM, for each exponent we take the maximum. Any other questions with that? Because yeah, this formula might seem like it comes out of nowhere. Okay, so let's work out what we would do for the GCD of 1200 and 2520. Okay, so we can factor 1200. We know there's 2 zeros at the end, which means we can right away take out 2 squared times 5 squared. Is that clear? Right? And then what do we have left? We have 12, which we know is 2 squared times 3. Okay, so that gives us 1 3, 2 5s, and 4 2s, which gives us our prime factorization 2 to the 4 times 3 times 5 squared. If we look at 2520, similarly, we can prime factor and we'll get 2520. Okay, you can take out a 2 and a 5 at the end because there's a 0. Then you're left with 2 5 2. You remove 1 2, you're left with 1 2 6. Remove another 2, and so on and so forth. Is that correct? Yeah, that is. Yeah.
Just to make sure I'm not confused. For the previous problem, you have 2 and then should that be 4 comma 3 or is it supposed to be 3 comma 4? If we're using like the A's and B's, like with the algorithm, the 16 is our A. Should it be 2 and then 4 comma 3?
I guess if you want to follow that, yeah. But the min of A and B is the same as the min of B and A.
Okay.
So yeah, but if you wanted to follow that exactly, then sure, I would have to write 4 and 3 in each of these places.
Because 0 and 1 is still 1.
Yep, you're right. You're right. Okay? And so to find the GCD and LCM, we sort of just apply this algorithm, right? So when we're trying to find the GCD, our potential exponents on 2 are 4 and 3. The min of that is 3, so we take 2 to the 3. The min of 1 and 2 is 1. Min of 2 and 1 is 1. And the min of 0 and 1 is 0. And so we multiply those out and we get 120, which is the largest number that is a factor of both 1200 and 2520. Okay, similarly, to find the smallest number that is a multiple of both 1200 and 2520, we take the max of each of these exponents. Any questions with this? Okay? When the GCD of two numbers a and b is equal to 1, what can we say? So when the greatest common divisor, so the largest number that divides both a and b is 1, what do we know? Yeah. Not that they're both prime, but not necessarily. So 9 and 25, their GCD is 1. But neither 9 nor 25 are prime. Right? Yeah, they have no common factors. Okay? So if the greatest common divisor of two numbers a and b is 1, it means they share no factors. Another equivalent way of saying this is that they're relatively prime. Okay? Share no factors other than 1. Right? We call this relatively prime. So again, it's not that they're prime themselves. So think of the example, the GCD of 9 and 25. 9 is 3 squared, 25 is 5 squared. So neither of them are prime, but they share no factors. So we say they're relatively prime. It's just like when you're trying to write some number as a fraction, in the reduced form, it's the one where the numerator and denominator share no factors. I.e., it's the one where the numerator and denominator are relatively prime. Is that clear? Any questions with this so far? Okay. So now here we go. So now we'll start formally talking about modular arithmetic, okay? And there's a reason we went over all the stuff we just talked about, and it's because it'll be useful in talking about modular arithmetic, okay? So the standard example that people use when introducing modular arithmetic is suppose the clock reads 5, okay? Let's ignore AM and PM for a second. And we want to know what time it will say in 13 hours, okay? Would you say 18? Probably not, right? What would you say? You'd say 6, right? And what did you implicitly do? You added 5 and 13 and took the remainder you get when you divide by 12. Is that clear? Just like if we started at, 7 o'clock and wanted to know the time in 352 hours, you wouldn't say 359. You'd find out whatever the remainder of 359 is when you divide by 12 and say that. Is that clear? So when we're dealing with modular arithmetic, you can think, or when you're dealing with the clock, you can think of all numbers on the clock as being equivalent to either 0, 1, 2, 3, 4, all the way until 11. Okay? So you can think of all numbers as being reduced to one of the numbers in this set. Is that clear? Okay. So formally, we say A modulo M, or A mod M, is the remainder when A is divided by M. Okay? So what would 12 mod 5 be? 2, right? So when we're dealing with mod 5, with numbers in mod 5, you can think of it as if there are only 5 possible unique numbers. 0, 1, 2, 3, and 4, which are the possible remainders when you divide by 5. Is that clear? Just like 0 to 11 are all possible remainders when dividing by 12, right? Either a number is exactly a multiple of 12, 1 away from a multiple of 12, 2 away from a multiple of 12, and so on and so forth. You can't have a remainder of 12 when dividing, because it would just be the next largest factor. Is that clear? Okay, so another equivalent definition is that we say A and B are equivalent, and remember, this triple equal sign carries over from where? Logical expressions, right? There we also use this triple equal sign to show that two expressions are equivalent. Okay? So here we say equivalent. So we say A and B are equivalent modulo M if, not sure that's what that's supposed to say. Sorry, this should say M divides A minus B. Okay? So we say A and B are equivalent modulo M if M divides A minus B. Okay? I.e. that A minus B is a multiple of M. Is that clear? Can someone sort of interpret this? How did I get that equation? Yeah.
So like A is essentially the remainder.
A is the remainder when you divide B by M.
Yeah.
Right? And I could also write this as A is equal to B plus KM. Here the K's would be different, i.e. they'd be negative 1 times each other. But that's fine, because here K can be negative. Right? I just said K has to be in the integers, not that it has to be positive. Okay, and why does this work? Well, it's because in either case, I can say either A minus B or B minus A is equal to some integer times M, telling us B minus A is a multiple of M, which is exactly what I said here. Is that clear? So an equivalent definition of modulo is that we say A and B are equivalent mod M if M divides A minus B. This is all just a fancy way of saying A and B have the same remainder when you divide by M. Is that clear? Cool. So as I mentioned earlier, when we're dealing with numbers modulo M, all integers, that's both positive and negative, and 0, can be reduced to one of the numbers 0, 1, 2, all the way until M minus 1. Okay? So suppose we're dealing in modulo 5. What is the set of all possible integers? Yeah. 0, 1, 2, 3, and 4. Every integer is equivalent to 0, 1, 2, 3, or 4. And how many integers are in that set? 5. Because there's 5 possible remainders when you divide an integer by 5. It's either 0, 1, 2, 3, or 4. Okay? So what we're saying is that every integer, negative 12,000 plus 15, or, 67,079, all of these integers can be reduced to either 0, 1, 2, 3, or 4 when we're talking about modulo 5. Is that clear? Okay? And so now suppose we have some number that's equivalent to A modulo M. We can add or subtract M as many times as we want, and these numbers will still be equivalent. The remainder, when you divide by M, will not change. Right? So suppose we have 3 modulo 5. The remainder when you divide 3 by 5 is the same as the remainder when you divide 8 by 5, is the same as the remainder when you divide 13 by 5, and so on and so forth. All of these numbers have a remainder of 3 when you divide them by 5. Is that clear? So all have remainder 3 when divided by 5. Is that clear? So if we have some number A modulo M, the number A plus M, A plus 2M, A plus 3M, and also the numbers a minus m, a minus 2m, a minus 3m, so on and so forth, are all equivalent. Is that clear? And why does that make sense? Suppose we have a plus m mod m. Well, what's the remainder you get when you divide m by m? 0, because m always divides m. So we can say this is equivalent to a mod m. And if we multiply m by any other integer k, this is not going to change, whether or not k is positive or negative. Is that clear? So any questions with all of this? So now let's take a look at some arithmetic operations in Module 1. Okay? So suppose we want to simplify 13 plus 14 times 6 in Module 5. We know the result is either going to be 0, 1, 2, 3, or 4. Is that clear? Right. So what we could do is multiply out 14 times 6. I think it's 84. Yeah, it's right there. And then you add those two, and you get 97. And you know 97 is 2 greater than 95, which is a multiple of 5. So our remainder is 2. But we also could have simplified things at first, right? We could have simplified 6 to be written as 1, right? Because we know the remainder when you divide 6 by 5 is 1. And we could also rewrite 13 and 14 as 3 and 4, right? So instead of multiplying out 14 times 6, I could have had 3 plus 4 times 1, and that gives me 7, which also gives me 2, right? So I get the same result. To reduce even one step further, I could have rewritten 13 as negative 2. Can someone walk me through why I could write 13 as negative 2? Yeah, sure.
13 minus 3 times 5 is just negative.
Exactly. To find, sorry, I guess I could put it like this. The following set of numbers are all equivalent modulo 5. Right? So I could do 13, 18, 23, 28, so on and so forth. But I could also subtract 5 as many times as I want. So I could go to 8, 3, negative 2, negative 7, in either direction, right? So the one I pick is negative 2 because it will make my numbers as small as possible. I could also pick negative 77 if I wanted. That's also equivalent to 3 modulo 5. But why? Because that would just make that would make our calculations more involved, right? I want to make the calculation as simple as possible, so I just find the smallest and closest numbers in modulo 5 and then do my arithmetic. So I rewrite 13 as negative 2, 14 is 4, and 6 is 1. And that gives me my answer right away. Negative 2 plus 4 times 1, which is 2. Is that clear? So this was just one example. What we need to show is, in general, that you can simplify your expression as you go, rather than waiting until the end to do it. So we say that if A and B are equivalent mod m, and C and D are equivalent mod m, then the two following relationships are true. A plus C and B plus D are equivalent in mod m, and A times C is equal to B times D, or equivalent to B times D in modulo. Is that clear? And so what that tells you is you can simplify your expressions as you go. Okay? And so you can sort of assume this is true for now, but we want to be a little more rigorous, and we want to prove that this is true. Okay? So the first rule, we know that if A and B are equivalent mod m, and C and D are equivalent mod m, then from what we saw a few slides ago, from this rule right here, we know that we can say B is the remainder, A is the remainder when you divide B by m, and C is the remainder when you divide D by m. Is that clear? I could also write this the other way. I could also write this as A is equal to B plus m k1, and C is equal to D plus m k1, or k2, I guess. The k1s and k2s would be different, but those are also statements that I could write. Right? And here, k1, k2 are integers. Not necessarily positive, but they're integers. Okay? Is anyone unclear on how I got these equations? Again, another way of looking at this is if A and B are equivalent, I know M divides A minus B. Also means M divides B minus A. And here I have B minus A is equal to M times some integer, which is exactly the definition of dividing. Yeah,
This is kind of a question for the previous slide.
sure.
So when you need to write mod, like you just write F.
Yeah, so it would be annoying to write mod 5 at every step, right? So as long as it's clear that you're working in modulo 5, you don't have to include it in every line. How I've done it here at the end of each line is okay. Is that fine? Cool. Any other questions? Cool. So I can write B is equal to A plus some constant times M1, and D is equal to C plus some other constant times M1. But now if I add my expressions for B and D, I get B plus D is equal to A plus C plus this M times K1 and M times K2. But then I can common factor the M out and I get M times K1 plus K2, right? Giving me that, like this expression right here, B plus D is equal to A plus C plus M K1 plus K2. That's exactly the form of these two equations, right? Which implies that B plus D and A plus C are equivalent modulo M. Is that clear? So I started off with that A and B are equivalent and C and D are equivalent. And I showed that if that's true, then A plus C and B plus D are equivalent. Meaning they have the same remainder when you divide them by n. Is that clear? And it's very important to write this triple equal sign because they're not equal, they're equivalent. In these expressions here, there I was talking about strict equality, not equivalences, but those were integer equations that were true, equal, regardless of any modulo, right? But here when I say A and B are equivalent, I need the triple equals. Any questions with this? Cool. And so the second rule, that the product of AC is equivalent to the product BD in modulo M, we'll put that on the homework. Okay? But it's very similar to what you just did here. You would write this relationship between B and A, and also write this relationship between D and C, and you would show that these two products are the same. Sound good? Okay. So another operation we need to talk about is exponentiation, right? So suppose we want to evaluate the number 2 to the 15 modulo 9. Okay? The naive way would be to expand out 2 to the 15, start at 2 to the 10 is 1024, multiply that by 2, then a 2 again, the 2 again, the 2 again, the 2 again, and you'd get 32,768. And then you could divide this number by 9 and find out the remainder you get. But there has to be a better way with modular arithmetic, right? So you notice that you can write 2 to the 15, because 15 is equal to 3 times 5, I can write 2 to the 15 as 2 to the 3 quantity to the 5. Is that clear? So I'm rewriting this cleverly. But since we're working with modulo 9, I know that 8 is equivalent to -1 modulo 9. Is that clear? Right? Because if I have 8, I can add 9 and subtract 9 as many times as I want. So I can go to 17, 26, blah, blah, blah. But I can also go to -1, -10, and so on and so forth. Is that clear? And so something you probably should notice is that -1 is always equivalent to n minus 1 mod n. Is that clear? Right? Why does this work? Because when you look at n minus 1, when we're dealing with mod n, the n is the same as 0. So I can replace the n with a 0, and I have -1. Is that clear? Okay. So using the fact that 2 to the 3 is 8, but that's equivalent to -1 in mod 9, I can replace my 2 to the 3 with a -1. And so now instead of having 2 to the 3 to the 5, I have -1 to the 5, which is just -1, right? But -1 is the same as 8 modulo 9, right? So when we do these expressions, we always want our answer to be, think of it as being in standard form, as in being one of the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, right? You can think of standard form as being one of the numbers in the range 0 to m of minus 1. So does anyone have any questions on how we got to that answer? 2 to the 15 modulo 9. Okay, another example, suppose I want to evaluate 5 to the 11 modulo 26, right? I can rewrite 5 to the 11 as 5 squared to the 5 times 5. Why is that the case? Because I can write 11 as 2 times 5 plus 1. Okay? But what is 5 squared? Ooh, this should be a negative 1 here. 5 squared is 25, right? Which is negative 1 modulo 26. Is that clear? So this should be a negative 1. Brackets should be around here. And that gives me negative 5 mod 26, which is, what's negative 5 in modulo 26? 21, right? Because it's what I get when I add 26 to negative 5. Is that clear? So this gives me 21 mod 26. Is that clear? So how I rewrote it was so that I could use the fact that 5 squared is negative 1 when we're talking about mod 26. Then I have negative 1 to the 5 times 5. Negative 1 to the 5 is just negative 1. Multiply that by 5, I have negative 5, which gives me 21. Similarly, 23 to the 9. I know 23 is 1 less than 24. So 23 is equivalent to negative 1 in modulo 24. And negative 1 to the 9 is just negative 1, which is, this should be a 23, I believe. Is that clear? Any questions at all? Okay. Now, what if we want to expand out something that's a little more complicated? So, for example, 4 to the 26 modulo 13. Okay? What we can use is the fact that any integer can be written as a sum of powers of 2. Okay, can someone reason to me why that's true? Why can we write any integer as the sum of powers of 2? Sure.
Because every integer is either odd or even, and one of the powers of 2 is 0, so if it's even, you can just keep dividing it by 2. And if it's odd, you can divide it by 2. You keep dividing it by 2 until you get to 1, and like 2 to the 0 is 1.
I see. Okay, I see what you're saying, but I'm asking why it can be written as the sum, not prime factored by 2's. Yeah.
To say that it's just the same as finding the binary representation of that number, so
exactly
that exists.
Right. We know that every integer can be written in binary, but binary has the special property that every digit is either 1 or 0, on or off, right? So if the digit is a 1, we include it in our sum, and if the digit's a 0, we don't include it in our sum. Okay? So that's only true for powers of 2, because if we look at, I don't know, powers of 3, when we write things in base 3, each digit is either 0, 1, or 2. So it's no longer just 0 or 1. So that's no longer true. But since we know that every integer can be written in binary, we know that every integer can be written as a sum of powers of 2. Okay? For example, 26, we can write it as 16 plus 8 plus 2. Out of curiosity, what does this mean, the binary representation of 26 is? It should be 1, 1, 0, 1, 0. Can anyone explain how I got that? Yeah.
This 2 to the 3rd, and
Exactly.
2 to the
Yeah. So the first digit is 2 to the 4. Second is 2 to the 3. Third is 2 squared. Fourth is 2 to the 1. And last is 2 to the 0. And since I know my sum is 16 plus 8 plus 2, which is the same as 2 to the 4 plus 2 to the 3 plus 2 to the 1, I know the digits in the fourth exponent, third exponent, and first exponent spots should be 1, and all of the others should be 0. Okay, but that's an aside. So I know that I can write any integer as the sum of powers of 2. Okay? So when I want to look at 4 to the 26, I can instead write it as 4 to the 16 times 4 to the 8 times 4 squared. Because 26 can be written as 16 plus 8 plus 2. Is that clear? So why have I decided to write it in terms of powers of 2? Because what I can do is something called repeated squaring. I can take 4, square it to get 4 squared, find out what that result is, square that again to find out what 4 squared is, 4 to the 4 is, square that again to find out what 4 to the 16 is, and so on and so forth. Is that clear? So I can start with 4 to the 1, find that, 4 squared, 4 to the 4, 4 to the, there should be 4 to the 8, 4 to the 16, and so on and so forth. Is that clear? Okay, so for example, if I want to write out the expansion of 4 to the 26, I can start off with 4 to the 1, which I know is 4. Okay? The first time I square it, I get 16, but since we're working modulo 13, I can rewrite 16 as 3. Is that clear? Okay? Now I want to find 4 to the 8, because that's the next term I care about. So I can write this as 4 to the 8, 4 squared raised to the exponent 4. Is that clear? And what's 4 squared to the 4? Well, that's just 3 to the 4, right? And so that's where the benefit comes in, because I can use simplified previous results, right? I already simplified 4 squared to be 3 in modulo 13, so I can plug in 3 for 4 squared. And then I look at 81, and I look at the remainder when 81 is divided by 13, right? 13 times 6, I believe, is 78. So this should be 3, right? That should be 3, yeah. Okay, because 13 times 6 is 78, and 78 plus 3 is 81. So that should be a 3. Okay? And now 4 to the 16 is whatever 4 to the 8 was squared. We know 4 to the 8 was 3, so this is just 9. Is that clear? So what we're doing is repeatedly squaring 4 squared, then 4 to the 4, then 4 to the 8, then 4 to the 16, so on and so forth. And we're using the fact that any integer exponent can be written as the sum of powers of 2, and then whatever powers of 2 we need in our sum, in this case 16, 8, and 2, we just include those and multiply them at the end. Is that clear? So our final result should now look like 4 to the 16 times 4 to the 8 times 4 squared. So it should be 9 times 4 times 3, right? So all of that's irrelevant now. But now my expansion looks like 9 times 12 mod 13. Can someone simplify that quickly for me? Oh, I think that should be 9 times 3 times 3. So this should be 3 times 3 times 9. Right? Yeah, okay? So can someone simplify 3 times 3 times 9 modulo 13 for me? So what's 9 times 3? 27, which is 1, because it's 1 greater than a multiple of 13, which is 26. So I can say this is 3 times 1 mod 13, which is 3 mod 13. Is that clear? So what we did is we rewrote 26 as 2 plus 8 plus 16, and then used this technique of repeated squaring to determine what 4 squared, 4 to the 8, and 4 to the 16 were. And we simplified as we went, making our numbers relatively small. Okay? The only reason you do this repeated squared thing is if you have to do it by hand. If you were to do this in the computer, you would just do 4 star 26 percent side 13, right? So this is for more of a how you do this by hand, or how you'd write an optimized computer function to do this. Sound good? And so yeah, this might seem weird the first time you see it, but you'll gain much more practice with this throughout the homework and whatnot. Yeah.
Question. How come on line 3, you said 3 to the 4 is 81, and then you wrote that as 3 mod, like 3, in terms of mod 13 is 3.
Yeah.
But then on line 4, you say 3 squared is 9. But then you don't just, aren't you supposed to mod that by 13 and then get 4?
No, so every number when we're talking about modulo 13 is equivalent to either 0, 1, 2, 3, ... all the way until 12.
Yeah.
So 9 is already the most reduced form.
True.
I think what you were thinking of was 13
Yeah.
mod 9, which would be 4
Yeah,
mod 9. Yeah. Good point. So any questions with that? Okay, so this is repeated squaring. So far we've talked about exponentiation, our standard multiplication and addition. Subtraction is just adding a negative sign to multiplication. Or sorry, subtraction is just adding a negative sign to addition, right? So what's the one thing we haven't talked about yet? Division, right? And so before I even go to the next slide, what do you foresee the issues might be with division? Yeah.
Division is not closed over the integers, so we might get some numbers that are not integers when we divide.
Exactly. When we divide two integers, we don't necessarily get an integer. But as we've mentioned many times today, when we're dealing with modulo m, we can consider all integers as being equivalent to either 0, 1, 2, ... to m minus 1. But the number 2 over 3, that's not an integer. So which one of these would that be? So immediately there's no obvious way to translate division over to modular arithmetic, because fractions essentially don't exist for us. We only care about integers. And all of our operations must take in integers and output integers as well. Is that clear? So does everyone see the initial problem that we might have when dealing with division? Okay, so let's tackle it. So before doing that, let's take a look at this induction problem, which previously would have been very tedious, but now with modular arithmetic is very easy. Okay, so the question is, prove that 11 to the n minus 6 is divisible by 5 for all n. Okay? So before, if we did this at any point before today, we would do this by induction, right? We'd say our base case is when n is equal to 1, and when n is equal to 1, we have 11 minus 6, which is 5, which is divisible by 5, of course. Then our induction hypothesis would be assume 11 to the k minus 6 is divisible by 5 for some arbitrary k. So equivalently, we could say that 5c is equal to 11k minus 6, right? Because if we're saying 11 to the k minus 6 is divisible by 5, we can write it as 5 times some integer. Is everyone with me so far up until here? Okay? And then in our induction step, we want to expand out 11 to the exponent k plus 1 minus 6. But we can write 11 to the k plus 1 as 11 to the k times 11. Substitute in what we had in our induction hypothesis, 5c plus 6. Right, so what we did here is we wrote 11 to the k as 5c plus 6 and plugged that in here and did some expansion, and we saw that we could write 11 to the k plus 1 minus 6 as 5 times some integer, right? And so by induction, we had it this time. If we assumed that 11 to the k minus 6 was divisible by 5, we showed that 11 to the k plus 1 minus 6 was divisible by 5. So that's how we do it before. But now, it really boils down to just being one line, right? If we're looking at, well, all we want to show is that 11 to the n minus 6 is equivalent to 0 modulo 5. Because if it's equivalent to 0 modulo 5, that means 5 divides it, i.e. it's a multiple of 5. Is that clear? Right? Because any number that's a multiple of 5 will be 0 modulo 5, because the remainder when you divide it by 5 is 0. So I know 11, when I divide it by 5, the remainder is 1. Right? So I can replace 11 with 1. And 1 to the n is always 1, right? Assuming n is an integer. So then I get 1 minus 6, which is negative 5. which if I add 5 to it, which I can do because 5 is our modulo base, I get 0. So right off the bat, one line, we don't have to do any induction or anything weird. So it saves us a lot of time when we're talking about questions like this. Right, but we didn't invent modular arithmetic just to do weird induction questions. There are more applications of it, as you'll see, perhaps in the homework and also in future courses, such as in cryptography. Okay? Okay, so this is an example of how modular arithmetic makes our life easier in some of these questions. Okay? And if you go back and look at the questions where we broke x into 3k, 3k plus 1, and 3k plus 2, those questions can be greatly simplified using modular arithmetic. Sound good? Okay, so back to what I was talking about before, division in modular arithmetic. Okay, so if we want to solve the equation 3x is equal to 14, so not equivalent, I'm just talking about regular vanilla grade school arithmetic, I would divide both sides by 3. But what I'm really doing is multiplying both sides by the multiplicative inverse of 3. Is that clear? Just like if you took 54, I don't know, you're trying to solve ax is equal to b, you multiply both sides by the inverse of a, if that exists. And you get x is equal to a inverse b. Okay? So over the real numbers, the multiplicative inverse of a number is defined as the number you multiply by to get 1. Right? And so for any number that's not equal to 0, that was just the reciprocal of the number, 1 over that number, right? Because x times 1 over x is equal to 1. Is that clear? Multiplicative inverse of a real number is just its reciprocal. Okay? But again, in modular arithmetic, the idea of 1 over a number doesn't exist, right? Because all of our numbers are reduced to 0, 1, 2, all the way until n minus 1, right? So this idea of dividing both sides doesn't quite work. So what do you propose we do? How do you think we can solve this issue of not having division with modular arithmetic? Sure.
You should change the exponent to negative.
What do you mean by that?
Like, if you had 1 over 8, you would just say 2 negative.
But that's still the same number as 1 over 8. Okay. Yeah.
If you try finding a number such that you multiply the number with that number, mod something, you get 1.
Exactly. So all we need with modular arithmetic is to find some other number that if you multiply, let's suppose I want to find the inverse of x mod m. I need to find some other number that when I multiply it by x, I get 1 in mod m, right? Because it doesn't need to be equal to 1, it just needs to be equivalent to 1 in mod m. That's exactly what we do. So we say y is the modular inverse of x in mod m if x times y is equivalent to 1. Is that clear? Okay? And you'll see in the next slide that this inverse doesn't necessarily exist. Okay? And that's something we'll explore more later next week and on the homework. When and when does not this inverse exist? Okay? So for example, suppose we wanted to find the multiplicative inverse of 3 in modulo 5. That means I'm looking for some number that when I multiply it by 3, I get 1 in mod 5. Okay? With 5 being our modulo base, it's not that hard to just guess and check. Because you know the answer either has to be 0, 1, 2, 3, or 4. Is that clear? So you could just iteratively go through. It's probably not going to be 0. So you could check 1, 2, 3, 4. Right? And pretty quickly you'd see when you multiply 3 by 2, you get 6, which is equivalent to 1 in mod 5. So we would say the inverse of 3 is equivalent to 2 mod 5. But if 3 is 2's inverse, then what is the inverse of 2? 3, right? Because when I multiply, it's the exact same definition. So the inverse of 2 is 3 mod 5. Because when I multiply 3 by 2 or 2 by 3, it doesn't change anything. The result I get is 1 in modulo 5. Okay? But for example, the inverse of 10 in modulo 12 doesn't exist because there's no solution to 10x is equivalent to 1 mod 12. Okay? You can either take my word for it, you can multiply, or you can plug in x is equal 1 to 11, or sorry, 0 to 11, and see that there's no value of x that gives you 1. But there's just no solution to that. Okay? So weird. This modular inverse doesn't necessarily exist. And so we saw in the real numbers, the only number that didn't have an inverse was what? 0, right? Because there's no number you can multiply by 0 to get 1. But here, with modular arithmetic, 10 is definitely not equal to 0. But it also has no inverse. So we have numbers that are not equal to 0 that has no inverse. Okay? So let's take a look at this. The problem of finding the inverse of a in modulo m can be reduced to finding integer solutions to ax plus my is equal to 1, right? Because all this says is that when you multiply a by x, you are 1 away from some multiple of y. Are there any questions with where that equation comes from? Also, if you were to take mod m of both sides, the my term would disappear because that's definitely a multiple of m, so it's equivalent to 0. So on the left side, I would have ax, and on the right side, I would have 1, which is exactly what we're trying to solve, right? So if we find integers x and y that satisfy this equation, we know that x will be the inverse of a in mod m. Is that clear? So here, we have x is equivalent to the inverse of a in modulo m. So for example, if we want to find the inverse of 3 in mod 5, it boils down to finding integer solutions to 3x plus 5y is equal to 1. Okay? One thing to note is that these solutions aren't necessarily, they're not unique, right? Here I found 2 comma 1, right? Because 3 times 2 plus 5 times negative 1 is 1, telling me that 2 is the inverse of 3. But I also could have found the ordered pair negative 3 comma 2, right? That's also equal to 1, telling me the inverse of 3 is equal to negative 3. But that's fine, because negative 3 is still equivalent to 2. So regardless of what integer solution you find, you can always add or subtract the modulo base as many times as you need to until you get an answer that's between 0 and m minus 1. Is that clear? Okay. And so how do you find this inverse? Well, for 3x, like the inverse of 3 in mod 5, it's not that hard to just try some numbers in your head and find the one that works, because there's only 5 possibilities, right? But suppose you wanted to find the inverse of 4 mod 73, you're definitely not going to sit there and check 0 through 72, right? So there has to be a better way, and that's called Euclid's extended GCD algorithm, okay? And so what that does is it provides a concrete way to calculate these coefficients x and y. And once you find these coefficients, x will be your inverse of a. Is that clear? And so in the homework, we'll have a relatively interactive question that walks you through how Euclid's GCD algorithm works, and it will give you practice with finding the inverses. So really quick, last thing, let's go back to this problem of finding the inverse of 10 in modulo 12. It's the same as finding integer solutions to 10x plus 12y is equal to 1. But we see that 10 and 12 happen to share a factor, right? What's that factor? 2, right? So what I can do is divide both sides by 2, and I get 5x plus 6y is equal to 1/2. And why is that contradictory? Well, because we said that x and y have to be integers, so that means 5x will still be an integer, 6y will still be an integer, and when you add 2 integers, the result should also be an integer. But what this is saying is that the sum of 2 integers is a fraction. There's no 2 integers that you can add and get 1/2, right? So what you notice is that if 10 and 12, or in general, if a and m share any factors, this inverse will not exist, okay? So the main takeaway is that the inverse of a in modulo m exists if and only if so this goes both ways. The greatest common divisor between A and M is 1. Is that clear? So, for example, is there an inverse of 4 in mod 26? No, because 4 and 26 share the factor of 2. But is there an inverse of 5 in mod 26? Yeah, because 5 and 26 are relatively prime. So, here's an interesting question. What type of number must M be in order for all numbers to have an inverse? So suppose I want to pick an M such that all other integers have an inverse modulo M. What does M have to be? Prime, right? So we see that if your modulo base M is prime, then all other integers will have an inverse in that mod M. Is that clear? And that's another concept that you'll see, throughout the homework and future classes. Okay? So we'll stop there for now. Slides and lecture videos will be posted by tomorrow. Homework should be up by Wednesday. Discussion on Wednesday will be going over the midterm. Solutions should be out by Wednesday, and grades should be out by the weekend. Okay?